Hello, this is lecture 9A, part 1, inverse trig. My name is Scott Grizzard from the University of South Florida. So, for a student suggestion, I am splitting, if I have two separate topics in the same lecture, I'm going to split them up. So, today's lecture 9A covers two topics that are split up into a part 1 video and a part 2 video. The first video is on inverse trig. The second video is on L'Hopital's rule. And both videos are assigned to the class as lecture 9A. Also, by suggestion, it's been suggested that I put some suggested problems on the lectures. So this is in the book. This is section 3.5. And these are the suggested problems for inverse trig, instead of just giving them to you all at once. Okay, so last time we were talking about inverses. And remember this thing where I had to make a choice. So, like, if I was doing x squared and I wanted to do the inverse, I couldn't do both because it wasn't 1-to-1 nor onto. I had to make a choice. For x squared, I chose to go from 0 to infinity to 0 infinity. So I chose my domain to be 0 infinity and my target to be 0 infinity. So then I had an inverse. So it's important to note that I made a choice, and it was just a choice. I could have chosen something else. Well, now we're going to look at the same thing. The trig functions, sine, cosine, and tangent, also have this problem where they're not 1-to-1 and onto. Now, tangent actually is onto, but it's not 1-to-1. So what we're going to do is, we need to define, we need to make a restriction. We need to make some choices. And the choice we're going to make is going to give us the ability to create an inverse. So let's look at the restrictions that we need to make. So we call them onto if every y gets used, and 1-to-1 if no y is used more than once. So, and the last time the big idea was f as a cosine if and only if. So this if business, and that is not a Scottism. That's an actual thing. If with the long f, or if and only if, means if and only if, and you can look it up in the dictionary. It's nice to have that on the Scrabble board. You have to be playing the extended dictionary though on Scrabble. It's not on the narrow Scrabble dictionary, but the extended dictionary you can. Anyway, this right here is cosine, and as you can see, cosine is not 1-to-1. It's also not onto. So cosine is defined. Cosine is defined from all real numbers to all real numbers. Okay? So it's neither 1-to-1 nor onto. So as we can see, cosine there is failing the horizontal line test, right? It fails it all over the place. Now, I want to define an inverse, which means I need it to be both 1-to-1 and onto. Well, onto is easy to fix. Right? So I can't reach 2. I can't reach -2. So instead of saying, oh, this is a problem, we'll just say, oh, we're not even going to try. Right? This is kind of like the little kid that goes, I can't do it. I don't care anyway. Sour grapes the rest of the thing. And we're just going to say, we only want to reach -1-to-1. So that fixes the onto problem. But I still have the 1-to-1 problem. Now, I can make some possible choices. One of those choices is to go from 0 to pi. So this right here, this choice here, would be to say, okay, let's take this zone right here for my x values. There they are. And if I choose these as my x values, right, I'm choosing the upper half circle. I can choose those as my x values, and now I'm 1-to-1 and onto, right? So I could choose that. But I don't have to choose that. I could choose some other things. So here's the whole function. This is the choice that I just said we can make, right? We have the endpoint. We've got 0 to pi with +1 and -1. But I don't have to make that choice. I can also choose this. This right here would be to go from pi, in my x space would go from pi to 2 pi. And that's valid. That's a valid choice. Right? I could define this is the info that I wanted to define an inverse on. Okay? That would mean that the inverse that I had for 0 in my inverse, right? 3 pi over 2 maps to 0. Therefore, 0 would map back to 3 pi over 2. I could make that choice. I don't have to make that choice. I could also go negative. If I wanted to go negative, it would look like this. And this would go from negative pi to 0. This would be my choice for cosine, the cosine star that would make me 1-to-1 and onto. I don't have to make that choice. I could choose something else. Let's say I chose a piece of this and a piece of this. That would look something like that. Right? So here what I've chosen is I've chosen to go from 0 to pi over 2. And now I've chosen to go to pi to 3 pi over 2. And of course, I can't include that endpoint. And this is a valid choice. This function right here is 1-to-1 and onto. So I could define an inverse for that. It wouldn't be pleasant, but I could. Okay, so let's look at the choice that we kind of, why we would want to make a particular choice. Okay, so again, if I wanted to define okay, so if I wanted to choose the cleaning up a little bit, if I wanted to choose to go from pi to 2 pi, right? This is the start here. I'm going around here. I'm going to make the choice that it's going to be this range right here. This portion of the circle is what I'm going to care about. That's that portion of the circle. And I could do that. There's nothing wrong. There's nothing mathematically wrong with making that choice. Well, I didn't have to choose that. I said I could go negative as well. So here what I'm going to do is I'm going to choose this half going in the opposite direction. So here I'm going to go negative. Right? Instead of going the usual way, I'm going backwards. And then I've chosen the second, the bottom portion of the unit circle here as to give my domain. So this is going to be that choice. And again, I could go a little crazy and choose something like this. So if I chose this piece right here from 1 to pi over 2, and then from pi to 3 pi over 2, that would be like choosing this piece here, and then this piece here, not including that endpoint there. So I could make different choices and still come up with a valid thing. But what do I want? Well, I want 0 to pi over 2 in, right? Because those are the acute angles, okay? And then I want no breaks in the middle. Well, if I choose to have acute angles, you know, that first portion of the unit circle from 0 to pi over 2 in it, and then I want no breaks, I'm stuck with the first choice, which is kind of the obvious one. You know, it's like, well, duh, why didn't you just say we're choosing this? Well, I kind of wanted to emphasize the fact that we are making a choice. And it's an arbitrary choice. So what I'm going to do is I'm going to define a new function. So this right here, right, this is my eastiness. Cosine measures my eastiness. And then the question my arc cosine or my inverse is going to ask is, if I'm negative square root of 2 east of the mascot's nose, or east of this line, how far did the runner run? Well, the runner had run pi over 2 plus pi over 4 in order to get to that point. So that's sort of the idea. The idea is that it goes backwards. So cosine is now going to be defined from 0 to pi to negative 1 to 1. And arc cosine is going to be defined from negative 1 to 0 pi. So the cosine star... Right, cosine star is the restriction. That's the technical term for it. And in particular, it's the 1-to-1 restriction, right? It's the one that makes this function 1-to-1, and it get the canonical. So we can say it's the canonical, or the usual, the one that everyone uses, restriction on cosine to make it 1-to-1. I'm calling it cosine star. And then arc cosine is defined as its inverse. Okay, so cosine star of pi over 2 equals 0, just like cosine star of cosine of pi over 2 is defined as 0. So arc cosine of 0 is going to be pi over 2. But note here, the cosine of 3 pi over 2 is also 0, right? I'm standing here, but cosine star of 3 pi over 2 is not defined. It's not in the domain. And because it's not in the domain, I can't, it's undefined. Okay. Why is it undefined? Well, it's not in the domain. Okay. Let's look at sine. Sine's not invertible. It's also neither 1 to 1 nor onto. We need to make a choice. The target, again, we're just going to restrict to negative 1, 1, which is the range of sines. And now we have something that's onto. Well, how do we make our choice for sine of 1 to 1? Again, we could do lots of things, right? But we want the first quadrant from 0 to pi over 2, and we want an unbroken domain. We want a continuous function. So we're going to choose this piece here, just like before. But then I can't choose this piece because that would make northiness, that would make this thing not 1 to 1. So what I'm going to do is cheat this piece if I want to make it continuous. But that means I got to go to negative pi over 2 and to pi over 2. So this is the piece I'm going to change. And I'm going to make it negative pi over 2 to pi over 2. So if we look at that on the graph, I'm choosing this right here is the graph of sine. And then I'm going to make the choice to go from something in here to something in here. Okay, so just like before, I've made a choice. And the choice I'm going to pick is this piece right here. So this is the whole thing. And I chose this piece right here, since that makes it 1 to 1 and onto. And includes this quadrant right here, which is what I want to include. Okay, so I make that choice, and I've got sine star is going to be go from negative pi over 2 to pi over 2 into negative 1, 1. And I'm going to define arcsine as the inverse of sine star. So again, if I've got sine star of 0 equals 0, arccosine of 0 equals, arcsine of 0 equals 0. Sine pi over 2 equals 1. So arcsine of pi 1 equals pi over 2. Sine of pi, again, equals 0, but sine star of pi is undefined. It's over here, and it's not in my domain for sine star. Okay. So we're doing the same thing we did before. All right, so now we've defined kind of a 1 to 1 and onto. And by the way, tangent, did I write tangent down? Tangent is going to be defined. Tan star is again, it goes to R. So it's already onto for R. I don't have to mess with the code of the target, but I do have to mess with the domain. So the domain is going to be basically the same as sine, except I don't have the endpoints. And some people want it to be infinity at the 2 lines. And if you so desire, you can. I'm not, but you can do that if you want to. All right, so there it is for tan. Now, question, how do we do derivatives of these things? Well, let's look at both of these. Let's look at arcsine as the first one, okay? So what I'm going to say, it turns out that the derivative of arcsine of x is 1 over the square root of 1 minus x squared. And that's just our derivative rule for it. So our derivative rule is simply d over dx is simply going to be 1 over the square root of 1 minus x squared. Okay, so for our example, if I want to do the derivative of this, I've got a u here. So I'm going to need a chain. The derivative with respect to u of arcsine of u is 1. And I'm going to wind up with 1 minus x to the 10th on the bottom because I had x to the 5th squared again. And be careful of that. So that's the derivative there. That's how I use the derivative rule. Okay. Now, how do I prove it? Well, what I'm going to do is I'm going to let theta, and this is a convention, right? So just as a convention, I am going to use y x, y, and z for sides, and Greek theta and sigma for any angles, okay? So sine and cosine take angles for input and sides for output, while arc cosine and arc sine take sides for input and output angles, give angles as output. Okay, so that's one of these little things, right? One of them, sine takes an angle and gives me back where a distance around the unit circle, and it gives me back the length of a side. Okay, that's how I'm going to think about it in my head. So x and y's are going to be sides, thetas and sigmas and alphas and betas. Greek characters are going to be used for and phis and things like that are going to be used for angles. Okay, so what I'm going to do here, I want the derivative with respect to x of arcsine of x. What I'm going to do here is I'm going to let theta equal arcsine of x. I'm just going to take the sine star of both sides. Then I'm going to implicitly differentiate with x. So it's sort of like logarithmic differentiation, or sort of like those power rule proofs, right? We want to, or sort of like the log proofs, right? We want to do something to both sides and then differentiate. And then I'm going to use this triangle trick to deal with cosine, and I'll give you that in just a minute. And I'm going to remember that cosine of theta is greater than 0 for the domain of sine star. That's going to be important. Okay, so let theta equal arcsine. Then sine star of theta is going to be sine star of arcsine of x. Okay, so I took the sine star of both sides. Now, these two are inverses. That means when I compose them, they just give me x. Okay, now I'm going to take the derivative of both sides with respect to x. I'm going to have a chain rule, and I wind up with the cosine of theta times d theta over dx on this side from the chain rule, and this is just 1. And that gives me d theta over dx equals 1 over cosine of theta. But I'm not actually done here. Okay, and by the way, that matches with what we had last time, where I would take, if I wanted the inverse, right? I'm looking for the inverse of sine, and the derivative should be 1 over the derivative of the other. But it's in terms of theta, not in terms of x. Okay, so this right here, that actually matches with what we had last time, right? So, you know, I've got 1 over the cosine, but now I need to put this in terms of x. Okay, so what I'm going to do is I'm going to use a little SOHCAHTOA on this sucker. Now, there is another way to do it, but let's just look at this triangle trick here. Okay, so here's the triangle trick. Since sine of theta equals x, and remember that sine equals opposite over hypotenuse. Well, wouldn't it be nice if that hypotenuse was just 1? Because if the hypotenuse was 1, then look what would work out. This x here, the sine of theta, would simply become x. Right, which matches what we had, right? Now I've got x over 1. And this a that I want to solve for is the cosine. And that's what I want, right? I want the cosine. So what I'm going to do is I'm going to say, okay, that means that a squared plus x squared equals 1 squared, right? That's Pythagorean theorem. And that gives me that cosine squared plus x squared equals 1. Well, that's fun. So now I get 1 minus x squared on the right-hand side. Now, if I take the square root, I'm going to have a little issue here, right? 1 minus x squared. Well, do I want the top or what do I want here? Well, do I want a positive square root or a negative square root? Or do I have both? Should it be plus or minus, right? Well, theta is between negative pi over 2 and pi over 2. By the way, I lost the endpoints back up here. When I had this, 1 over cosine of theta, that's where I lost those 2 endpoints. Right, because the eastiness of the 2 things is 0, and this would get left me dividing by 0. So I can't have a derivative defined at the 2 endpoints for arcsine. Now, here I'm going to have, so the cosine of theta is greater than 0. Well, if that's the case, then I just take the positive bit. And I get cosine of theta equals the square root of 1 minus x squared. Okay. So d theta over dx equals 1 over the cosine of theta, which equals 1 over the square root of 1 minus x squared. So that's dy over the derivative of arcsine is 1 over the square root of x squared. Now, there is another way to do it. The other way is when you get to this point here, I can use the Pythagorean identity on that. Instead of using the triangle. It's the same thing. It's just a little bit, if you like the algebraic cleanness of it, more power to you. Okay. Now, the derivative of arccosine is negative 1 over the square root of 1 minus x squared. And doing that proof, it's basically the same proof. Okay, so if you review this proof, and it is in your book, by the way, too, if you review this proof, you can come up with the proof of arccosine by following along with this proof, substituting in cosine where you see the sign. And then you'll have a negative pop out at you when you do the derivative of cosine. Just hold on to it. You're going to need it in a moment. Then you do the triangle trick again, or you use the Pythagorean identity. And you'll wind up with this as your final answer, except, of course, with cosine and a negative on top. Okay. Let's look at tangent for a moment. The derivative of tangent is 1 over positive 1 plus x squared. And so what I'm going to do is I'm going to do the same kind of setup where I take tan star both sides and then implicitly thing, but my triangle trick's going to be a bit different. Okay, so here's my triangle trick. I've gotten d theta over dx equals cosine squared of theta. Because remember, the derivative of tangent is 1 over cosine squared, right? It's secant squared. So I wind up with d theta over dx being cosine squared of theta. Okay, but d theta over dx, this is in terms of theta, and I want something not in terms of theta. I want something in terms of x again. So I'm going to do the trick I did before. My opposite is going to be x, right? So TOA, tangent is opposite over adjacent. So I'm going to make this my x. I'm going to make my adjacent 1. And I'm going to leave my hypotenuse as c. Well, tangent is x over 1. Cosine is the adjacent over the hypotenuse. So it's going to be 1 over c. Right? So cosine is going to be 1 over hypotenuse. Okay. So now I do the Pythagorean theorem again. I get c squared equals x squared plus 1, which means that 1 over c squared is going to be cosine squared. Well, cosine squared is 1 over x squared plus 1 then. Right? Because now I've got cosine is 1 over c, and this is 1 over c squared, so I'm going to get cosine squared. Okay? So 1 over c squared that came from that. This right here is because this is adjacent over hypotenuse. Right? This is adjacent squared over hypotenuse squared. So my cosine squared of theta equals 1 over x squared plus 1. That means that my d, this is horrible. dx equals 1 over and there's my final answer. Okay, so these proofs, as I said, are in the book. Go ahead and review them. You can also do them for arcsecant, arccosecant, and arctan, but we're not going to. We're just going to stick with sine, cosine, and tangent. Okay, and that's it. So that's how you deal with the inverse trig. Hang out. Remember that part 2 of this lecture, L'Hopital's rule, is a separate video.